Oh, hey, welcome back. Now, this is the test 3 review for chapter 9, and it's all about sequences and series, right? Okay, so we started out in 9.1 just looking at sequences and worrying about the end behavior of sequences, and some definitions, the strict definition of a limit, some ways to figure out whether limits existed. So in the first set of problems, I'll be basically looking at limit problems. So you're determining whether the sequence converges or diverges. So for instance, a sub n equals 5 all over n plus 2. Okay? So we learned that basically anything from calculus will apply in this setting. So we can take the limit of this thing as n goes to infinity. It'll behave just like if you're taking the limit as x goes to infinity of 5 over x plus 2. Okay, so this form right here is L over infinity, which of course will be 0. Right? Okay, let's try another one, number 39. So we have a to the n equals n to the p all over e to the n, where p is greater than 0. Okay, so we try taking the limit as n goes to infinity of n to the p all over e to the n. This thing will be in form infinity over infinity. Okay, so if we're in the real numbers, we could do L'Hopital's. We're not technically in the real numbers, but we'll pretend like we were. Okay, so I'm going to do L'Hopital's in the top and bottom. Taking the limit as n goes to infinity, I'll have p n to the p minus 1 all over the derivative of e to the n, which is just e to the n. And I'm in no better shape, right? I'm still in an infinity over infinity kind of scenario. But if you have any experience with these, you know all you have to do is keep taking the derivative, and eventually this numerator, the variable, will go away. Okay, so it's like if you have y equals x cubed, you do y prime is 3x squared, y double prime is 6x, y triple prime is just 6. In other words, the variable is kind of annihilated. Okay. How many times do we have to take the derivative for this to happen? Well, if there's exponent of 3, it looks like you have 3 derivatives to do, and exponent 4, you'd have 4 derivatives, etc., etc. So it looks like here we'll have the limit as n goes to infinity. You're going to have to do basically L'Hopital's p times, right? And you'll end up with p factorial all over e to the n. And then finally, that is your L over infinity form, which again will be 0. And I should have noted these are convergent. Okay, so hence the sequence converges here and also down here. So hence the sequence converges. So if the limit does not exist, or if it goes to infinity or negative infinity, you'll say it's divergent. Okay? Let's look at one more example. So this one is a little bit different. You have to use a squeeze theorem on it. So we have a sub n equals sine of n all over n. And we'll sort of wedge sine of n into its traditional boundaries, right? So sine of n is definitely less than or equal to 1, greater than or equal to negative 1. And then we could divide all 3 sides by n. So you get negative 1 over n less than or equal to sine of n over n, and then less than or equal to 1 over n. Then you could take the limit on the outer parts, right? So note, number 2, the limit of negative 1 over n, of course, is L over infinity. That's 0. Also, then the limit of 1 over n is 0. Hence, by the squeeze theorem, the limit of sine of n over n is also going to be 0, and hence the sequence is convergent. Okay. So we had the squeeze theorem. There's also the even and odd thing. So if you can find that the even terms are going one place, but the odd terms are going somewhere else, that'll also imply the limit does not exist. We have the monotonic bounded theorem in there. We're not going to worry about that on the test, though. That's more of an advanced calc thing, so we're going to leave that for the future if you keep on taking math, okay? Okay, so 9.2, we start looking at the particular types of sequences that are important in our study. Okay, 9.2, we get our first sort of introduction then to the telescoping and geometric series. Okay, these are then related to the development later on, where we are trying to show that basically sequences of polynomials will converge to a function. Okay. Anyways, looking first at like a telescoping series, we have the sum from n equals 1 to infinity of 4 all over n times n plus 2. So with one of these, you kind of look at it and you can think, okay, I could probably do a partial fraction decomposition on the terms of that series, so that's kind of what you do. So let's go down here a little bit and pull that off. And I'll multiply through by n times n plus 2. We end up with 4 equals a times n plus 2 plus b times n. And then do your substitution, so let n equal, I guess, 0. So you get 4 equals 2a, and then a equals 2. And then plug in n equals negative 2, and you'll get 4 equals 0 minus 2b. So b is negative 2. And then we can go ahead and rewrite this expression. I'm going to factor out the 2, right? So I'll have 2 times 1 all over n minus 1 all over n plus 2. Okay. Then I'm going to rewrite it as a limit. So you can always rewrite an infinite sum as the limit, and we'll use the letter k. Goes to infinity of n equals 1 to k of 2 times 1 over n minus 1 over n plus 2. Then we're going to expand this thing and look for a nice cancellation. So the limit as k goes to infinity of the sum. We want to expand it, so let me get rid of the sum symbol. I don't need that anymore. Okay. So we have, there's a 2 floating about, so that's kind of factored out of this sum. You could do that now because it's finite. And you'll have 1 all over 1 minus 1 all over 3 plus 1 all over 2 minus 1 all over 4. Just get a couple terms until you can kind of see the pattern. So this will be 1 over 3 minus 1 over 5, maybe one more. 1 over 4 minus 1 over 6. And of course, that goes on and on forever until you get to the last 3 terms. So I'll do k minus 2. So n equals k minus 2 here. That will be 1 all over k minus 2 minus 1 all over k minus 2 plus 2 is just k, plus 1 all over, and so n equals k minus 1 now. So I have k minus 1 minus 1 all over k minus 1 plus 2 is k plus 1, and then plus 1 all over, where n equals k this time, k minus 1 all over k plus 2. Okay, so then you look for the cancellation pattern. So it looks like the 1 isn't going to cancel, but the 1/3 will cancel with this guy. Then the 1/2 won't cancel. So it's always the second term is skipping 1 parentheses and then canceling ahead. So the second term will skip, cancel, second term skips, cancels, and you'll get these guys canceling, and the 1/4 is gone. And then back here, you'll have these guys. So the second guy will skip that guy and cancel this one. Then the one from here will skip this guy and cancel this one. And then this guy here, negative 1 over k, will skip that guy and cancel that one. And then you're just left with what you have there. Okay, so this will end up being the limit of 2 times 1 plus 1/2 minus 1 over k plus 1 minus 1 over k plus 2. Okay. As k goes to infinity. And the k terms, the 1 over k plus 1 over k, those will just go to 0. Okay. So those will both be 0. And then you'll have 1 plus 1/2 is 2 halves plus 1 halves is 3 halves. And then it's just 2 times 3 halves, which is 3. Okay. So this thing adds up to 3. Right. Usually, we can't do that with series. we just have to kind of settle for approximation and knowing that the thing is convergent. But this was, in the beginning, we were just kind of throwing at you some series that actually worked out easily. So the other type that worked out easily was the geometric series. So geometric series just has a form n equals 0 to infinity of ar to the n. And that will equal a over 1 minus r when the absolute value of r is greater than 0 but less than 1. You can't, 0 it'll be convergent, but then you can't use the formula. Okay, so that's kind of a weirdness. And then it'll be divergent when absolute value of r is greater than 1. Greater than or equal to 1. We prove that in the videos. Okay, so there's a lot of different kinds of versions of this problem, but the one I kind of liked when I was just going through picking out problems were these kind of problems, right? So you can always kind of figure out the fraction form by using these geometric series. So you expand it. 0.12 repeating is 0.12 plus 0.0012 plus 0.000012, etc. Right? So the first term is a. It always has that form a plus ar squared plus etc. Right? And you can see that if you just plug in 0 into here and then plug in 1 and then plug 2, you'll get that form. So the a value, and we know it's going to be. And these kind of problems are always convergent, so that we don't have to worry too much about that part. But the a value we need to figure out the ratio, right? So the a value is 0.12. The r value is just a ratio of two consecutive terms. So you have 0.12 all over 0.0012. If you do some quick math there, that'll be 1 over 100. And so you know, this thing will be the series from n equals 0 to infinity of a, which is 0.12, times r, which is 1 over 100, to the nth power. And of course, now you really see, all right, this definitely is convergent because the absolute value of r is 1 over 100, which is definitely less than 1. Okay. So this thing will equal 0.12, the a value, or if you'd rather, 12 over 100, all over 1 minus 1 over 100. Okay. Get that out of the way. And then you could simplify that and have your answer. So this is 12 over 100 all over 99 over 100, which would equal 12 over 100 times 100 over 99, which would be 12 over 99, which would be apparently 4 over 33. Now you can check that in your calculator, but it does turn out to be our answer du jour. Okay. Okay. So, anyways, let's move on to 9.3, and we start getting this onslaught of tests. So in particular, you're not, like, again, you're not going to be able to figure out the actual sum, but you will be able to tell if it's convergent or divergent. And of course, then later we learned that we could just use the first couple terms of the series to make an approximation. So anyways, 9.3 introduced us to the integral test and to the p-series. So looking at problems like 3 to the 21 odd, and then problems like 33 to 37 odd. I wanted to look at this one because usually it gives people trouble. They want you to use the integral test to determine if it's convergent or divergent. On the test, I only need you to show that it's decreasing for it to work. So usually for the integral test, you need to show that it's positive and continuous and decreasing. But I'll allow you to assume it's positive and continuous, but then show it's decreasing. Okay, so your first step is kind of like, I have to show it's decreasing. How do I do that? Well, you take its derivative. Okay, so anyways, let's look at 13 as the problem in particular. I'm going from n equals 1 to infinity of arctan of n. And then that's all over n squared plus 1. So I consider then the function f of x equals arctan of x all over x squared plus 1. Okay. I'm going to get the derivative of that guy. I'm going to have to do low d high minus high d low, that sort of stuff. So f prime of x is low times the derivative of the high. The derivative of arctan is 1 over x squared plus 1, or 1 plus x squared, whichever you like, minus low d high minus high d low. So that would be the derivative of the low is 2x, and you just leave the high alone. Okay. All over the low squared. Okay. These guys will cancel, and you'll be left with 1 minus 2x arctan of x all over x squared plus 1 squared. And we have to compare that to 0. In particular, to show it's decreasing, this needs to be less than 0. So on a test, I would need to see your derivative and your inequality. Okay, whether you believe it's true or not, you better show it that way. It should better be less than. So the people are going to want to know why, though, right? If they question you any further, well, I just know it's probably decreasing because all the problems in the book are like that. No, you really would have to show this. I mean, like I said, on the test, all you have to do is get the derivative and put in the inequality less than 0, and I'll be done. But let's take a closer look at this problem, right? So the denominator is good to go. That's going to be positive no matter what. The numerator then, kind of, we're hoping it's going to be negative, right? So you take a closer look at the pieces of the numerator, in particular, the first look at the arctan. So I note arctan itself is an increasing function. And that's because of its derivative. It's always positive. Note y equals arctan is increasing, so y prime, because y prime is equal to 1 all over 1 plus x squared, which is always going to be a positive over a positive for any x values. Okay, in other words, its derivative is greater than 0, and therefore is always increasing. Okay, so great. Well, what else? Also then, I know the value of arctan when x is equal to 1. So also note then the arctan of 1 is equal to pi over 4, and pi over 4 is greater than 1/2. Okay. So in other words, for x greater than or equal to 1, we know then that arctan of whatever x, because it's always increasing, will be greater than 1/2. Okay. And then I can do even better than that. I could say 2. Just multiply both sides by 2, and I get 2 arctan is greater than 1. Okay. And then what else? Well, I can multiply both sides by x, and I get, so long as x is greater than or equal to 1, that's not going to change the inequality direction at all. So we get 2x arctan of x is greater than x. Okay. And of course, because x is greater than or equal to 1, I know that this must be then greater than or equal to 1. Okay. So anyways, I can move the x to the other side of this inequality. I could say this is 2x arctan of x minus 1, and then that will be greater than 0. Okay. And then I'll have then 1 minus 2x arctan of x is less than 0. Okay, which is what I was trying to show, because the denominator is definitely greater than 0. That means I need a negative in the top for this entire expression to be negative, and that's kind of what I have here. Okay, so I've shown that that numerator is negative, and therefore for x greater than or equal to 1, this will be true. Okay, so you don't have to show that whole end part there. That's just in case you were interested. Right. So once you've taken the derivative and you make the statement it's less than 0 and therefore decreasing, you can go ahead and do the integral test. Okay, so you have the integral. We're going from 1 to infinity of arctan of x all over x squared plus 1 dx. Okay. And then we're going to go ahead and change that into the limit as x goes to, or you don't use x, use some generic variable, like b. The limit as b goes to infinity of the integral from 1 to b of arctan of x all over x squared plus 1 dx. You do a u sub for arctan. Okay. We get a nice little cancellation out of it. Don't forget the limit. So we have u all over x squared plus 1 times 1 plus x squared du. Okay, so you see the nice cancellation. It's just going to leave us with something in terms of u. So we have the limit of the integral of u du from 1 to, well, we don't know what the limits are because we're in terms of u. So just go ahead and integrate that. So the limit of u squared over 2, remind yourself to evaluate. Then we could back substitute, so we end up with the limit of arctan squared x all over 2 from 1 to b, and finally we can replace all the numerical stuff, the variables and stuff. So evaluating, I'll have arctan squared of b all over 2 minus arctan squared of 1 all over 2. Okay. So where does arctan go as b goes to infinity? Well, arctan has those asymptotes. So as b goes to infinity, arctan is just going to get really, really close to pi over 2. Okay. Arctan squared will also do the same thing. It'll just go there. Arctan squared. So you really think of it as, finding the limit of arctan and then squaring that limit. So if you'd rather, you can kind of think of it as figuring out the limit of arctan as b goes to infinity, and then when you get that, you square it. So you're going to end up with pi over 2 squared all over 2 minus, and then arctan of 1 is just pi over 4, and then we square that over 2. And then this will be pi squared over 4 over 2, which is pi squared over 8. And then this will be pi squared over 16 over 2, which will be pi squared over 32. And then find a common denominator of 32. So I multiply this guy top and bottom, the first guy by 4. So you get 4 over 32. And then subtract and get 3 pi squared over 32. In other words, hence both converge. It doesn't mean they both converge to 3 pi squared over 32. No, that's not it. It's just that they converge. Okay. 9.4 gave us the comparison tests. So I'll be looking at questions like 5 to 25 odd. And number 7. Okay. So I'm going from n equals 2 to infinity of 1 all over the square root of n minus 1. And I want you to show it just the way I show it with 3 steps. So first you make your inequality. Okay, so I'm going to compare this to 1 all over. Usually what you do is just cut off one of the terms, right? So just get rid of the minus 1 and you're comparing it to 1 over square root n. If you do that, what you've actually done is increase the denominator, so you've decreased the overall expression, and the guy on the left will be bigger. Okay. Then you make a statement about the guy that you just made. So the series of 1 all over square root of n, which is a series of 1 all over n to the 1/2, is a p-series, where p is 1/2 and it's convergent. Okay. So thirdly then, sorry, p is 1/2, so it's divergent. Sorry. It wouldn't have worked if that was the case. You'd have to go back and try a different inequality. So if the guy on the bottom is divergent, it forces the guy above it to diverge, and then hence you could say both series have the same behavior, so both diverge. Okay. So you need to show me your inequality, talk about the series you're comparing it to, what type is it, what's the criteria, and is it convergent or divergent? And then finally make your conclusion. Let's look at 23. This time we have 1 all over n times the square root of n squared plus 1 from n equals 1 to infinity, and going to do a limit comparison test. So first, talk about what series you're going to compare it to. So I'm going to limit compare with 1 all over, just chop off the first, this part here, just use that. So it'd be 1 all over n times the square root of n squared. It's this series. And then you could simplify that into 1 all over n times n, which would be n squared. And then tell me, what kind of series it is. It's a p series. And then because p is 2, it's convergent. So I need to see all of that information. And on the test, I'll be telling you which test to use. So I'll say using the limit comparison test, determine if this thing converges. For this one, using the direct comparison test. To this one, I'll tell you to use the integral test. Okay? So it's not like I'm going to be throwing random series at you and expecting you to figure it out. Anyways, the second step for this test is to take the limit of the ratio of the terms of the series. So you're going to go the limit of 1 all over n plus 1 times these, sorry, I'm trying to do a ratio test or something. Okay, so just take either series and put it up top. I'll use 1 all over n times the square root of n squared plus 1, and then divided by 1 all over n square root of n squared as n goes to infinity. Okay, rewrite that, and you get the limit as n goes to infinity of 1 all over n times the square root of n squared plus 1 times n all over n square root of n squared all over 1. And of course, you don't need to write n square root of n squared. It's silly. Just put 1 over n squared. I don't know why I was doing that. Okay, and then we take the, multiply those together and take the limit. So we have n squared all over n times the square root of n squared plus 1. So this will be the limit as n goes to infinity of basically just this part of it. Okay, so you can still do that kind of chop off the first part technique, and you get n squared all over n times the square root of n squared, which again is n squared. So this will just be the limit of 1 as n goes to infinity, which of course is 1, which is greater than 0 and finite. Those two conditions have to hold for it to be a working limit. And in this case, then, if the other series is convergent, they're both convergent. Okay. One factoid in particular that people always screw up is that they think because it has a limit, it automatically converges, but that's not true. It's always dependent on the series you're comparing with. If the series you compare with is convergent and you get a limit out of it, then both will converge. If the series if your series you're comparing with is divergent, and you do this limit thing and it equals some number, in other words, it's convergent, it's still, both are divergent. Okay, so it's a little weird that way, but just kind of don't invent your own rules. Okay, you have to kind of go with the program. Okay. Okay. So anyways, the next section is 9.5. We're looking at problems like 9 to 23 odd, and in particular, let's look at number 17. It's a series from n equals 1 to infinity of negative 1 to the n all over the square root of n. We want to try the alternating series test. So try the alternating series test and note. Okay, there's two steps, right? So first we have to do the limit, and we're not looking at that negative 1 part. So a lot of people want to put that negative 1 thing in there. No, it's just the a sub n portion. It's always, the form is negative 1 to the n times some a sub n thing. And so the a sub n portion is the 1 over square root of n. Okay? Okay, so the limit of this thing is L over infinity form, that's 0. Secondly, then, we have to consider whether or not it's decreasing. And so I'll do sort of a ratio of a sub n plus 1 and a sub n and show that's less than 1. So this, if you rewrite it and multiply by reciprocals, you end up with square root of n all over the square root of n plus 1. And for n values greater than or equal to 1, certainly that thing, you have something bigger in the denominator than in the numerator, so it'll be less than 1. Okay? Hence, it's convergent by the alternating series test. Okay, we're going to skip out on the estimation part because sometimes that requires a bit of calculation, and usually I wouldn't let you even use a calculator, so that's why I skip those sections on these tests. But hopefully you did some in the homework and you're mildly competent with that kind of stuff. Let's look at 9.6. We got problems like 17 to 35 odd, and now we get into the ratio test. Which is the workhorse of doing a radius of convergence later on. So let's look at problem 30, which looked kind of unusual. N equals 1 to infinity of 2n factorial all over n cubed. Okay, so we have r equals the limit as n goes to infinity of the absolute value of, and now we replace n with n plus 1. So I have 2 times n plus 1 factorial all over n plus 1 cubed, times the reciprocal of a sub n. Okay, I'm going to rewrite that. The first guy is 2n plus 2 factorial. And I'm going to group that with the 2n factorial, and then times n cubed all over n plus 1 cubed. Okay. Then we can rewrite 2n plus 2 factorial as 2n plus 2 times 2n plus 2 minus 1, which is 2n plus 1, times 2n times 2n minus 1, dot, 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 3 times 2 times 1. All over 2n factorial is 2n times 2n minus 1 times 2n minus 2, dot, 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 all the way to 3 times 2 times 1. And then times n cubed all over n plus 1 cubed. Okay. Some nice cancellations somewhere. Oh, right here. 2n and down. Those guys are gone. So we have the limit as n goes to infinity of 2n plus 2 times 2n plus 1 times n cubed all over n plus 1 cubed. All we need is the high degree terms to figure out our limits, right? So here the trick for doing these, you just kind of pick out this guy times this guy times this guy, and that will give you the first term of your polynomial. So what is that? 4n squared times n cubed is 4n to the 5th. And then the bottom, all you have to do is kind of take n and cube it, and that'll give you the first degree term. The first term in the polynomial is n cubed. Oops, let me go back to white. If you need to, you can FOIL the heck out of that and get your answer, but ultimately it's going to be the limit of, looks like 4n squared, and that'll just go to infinity. So remember the criteria for the ratio test. If r is greater than 1 or equal to infinity, it's divergent. So hence in this case, r is greater than 1 or equal to infinity. So hence the series diverges here. Okay, so we did all this work, and we're thinking about just looking at numerical series. Ultimately, though, we wanted to connect this to functions and sequences of polynomials and that sort of stuff. So that then comes up in the next section, 9.7, where we're talking about polynomials and their relationship to these functions. We have the Taylor polynomial, the Maclaurin polynomial. Maclaurin polynomial is centered at 0. We're looking at questions like 17 to 31 odd, and basically you'll be producing the Maclaurin polynomial or Taylor polynomial for a given function. So let's look at 21. We have f of x equals x e to the x, and they tell us they want degree 4, and they say it's Maclaurin. In other words, c is 0. Okay, so I need to get the first 4 derivatives, evaluate them all at 0, and then put them into my polynomial template. Okay, so we have x e to the x, first derivative, leave x alone, times e to the x, plus take the derivative of, leave x alone times e to the x, because e to the x is the derivative of e to the x, right? And then plus, then take the derivative of x, which is 1, and leave e to the x alone. Okay, for the second derivative, you're basically going to get the derivative of this, which we already know is x e to the x plus e to the x, and then plus the derivative of this part, which is just e to the x, right? So you end up with x e to the x plus 2e to the x. And that kind of process will continue, right? The derivative of this will be x e to the x plus e to the x, and then the derivative of this will be 2e to the x. So you'll end up with x e to the x plus e to the x plus 2e to the x, which is plus 3e to the x. And then you could guess the pattern. Plugging in zeros, we get 0, 1, 2, 3, 4. Okay, so we want p sub 4. And I like doing the little boxes. You can do that too on the test if you want. And just copy and paste the 0, 1, 2, 3, 4, 0, 1, 2, 3. If you want to leave it that way, that's fine. You can simplify, though. It's probably, simplify it. That's what we always do here in math. So it looks like the 2's will cancel, and you get x squared plus 1 factor of 3 will cancel the denominator, leaving you with basically 2 factorial left, or just 2. So plus x cubed over 2. And then 4 will cancel with the first 4, because 4 factorial is 4 times 3 times 2 times 1. So you get that first 4, the cancel, and you're left with 3 factorial in the denominator. Okay. Let's look at a Taylor version. Okay. For the square root of x. We want the second degree polynomial approximation and centered at 4. Okay. So I need up to the second derivative. I'll start with f of x equals x to the 1/2. F prime of x equals 1/2 x to the negative 1/2. F double prime of x is negative 1/2 times 1/2, so negative 1/4 x to the negative 1/2 minus 2/2 is minus 3/2. Then evaluate. Okay, so 4 to the 1/2 is 2. This will be 1/2 times 4 to the negative 1/2, which is 1 all over 2 times 1 all over the square, 4 to the positive 1/2, which is 2. So that'll be 1/4. And the last guy, negative 1/4 times 1 all over 4 to the positive 3/2, which is negative 1/4 times 1 all over 4 to the 1/2 is 2, and then 2 cubed is 8. So this would be negative 1 over 32. Then we could go to our template, so p sub 2. This will be blank plus blank x plus blank x squared over 2 plus blank x. Well, that's as far as, and I got to be careful, right, because this is the shifted version. This is a Taylor. So I can't just write x. I have to write x minus the center. Okay. So what numbers did I have? 2, 1/4, negative 1/32. Okay, let's write that to make it, because I like to make things look nice. So 2 plus 1/4 times x minus 4 minus 1/64 at the end of the day times x minus 4 squared. Okay, next section then, ultimately what we want to do is take these polynomials and make them infinitely long. It's basically, if you do a sequence of these polynomials, and you take the limit of it, you get an infinitely long polynomial, and those are called power series. And we need to know for what values of x do they actually kind of work. Where are they convergent? So the end result of all of that business is 9.8, and we're using the ratio test in order to determine the intervals of convergence or divergence for power series. Okay, so let's look at one of those. And there were three cases. Either it's going to be divergent everywhere except at 0, or it'll be convergent everywhere, or it'll just have some radius of convergence. And the hard ones are usually when you have a radius of convergence, so I want to look at one of those. First off, to make things a little bit easier, I'm going to rewrite this and pull out the -1. Because when you go to the ratio test, you can kind of ignore the -1s floating about. So you could rewrite this as -1 to the n times 2x to the n minus 1. Or -1 to the n minus 1, rather. So, sorry about that. I'm going to rewrite this. Right. Okay, so I'm going to go to my ratio test and take a look here. So I have the r is the limit as n goes to infinity of the absolute value of n plus 1 all over n plus 1 plus 1 was n plus 2 times 2x to the n plus 1 minus 1 is n, then times the reciprocal of a sub n. And note, I didn't include the -1 to the n minus 1. No. You don't need it if you have the absolute values. Okay. Now consider the reciprocal of a sub n, which would be n plus 1 all over n times 2x to the n minus 1. Okay, and then I got some simplification to do here. So what do I have? N plus 1, basically squared, all over n times n plus 2 times 2x to the n minus parentheses n minus 1, because what? We have that thing, right? So that's just going to be 2x to the first power, which is just 2x. That's from this stuff. That stuff is this stuff, which turns out to be this thing, which I then go ahead and plop right there. Okay. Okay. You can factor out the 2x part. Absolute value of 2x is 2 times the absolute value of x. Then you have the limit of this thing, and if you wish, you can FOIL it out. N squared plus 2n plus 1 all over n squared plus 2n. And then the limit of that thing, is just the limit of n squared over n squared, which is 1. So you just end up with 2 absolute value of x times 1, which is 2 absolute value of x. Okay, so these things will converge when r is less than 1. Okay? In other words, when 2x is less than 1 but greater than -1. In other words, when x is between 1/2 and -1/2. Not done. Okay. I need to check the endpoints. So you need to check x is -1/2. So you're looking at, what was the original series, right? So the series n equals 1 to infinity of n all over n plus 1 times -2x to the n minus 1. Okay. So you're just, wherever you see x, you're putting in -1/2. So we have then the sum of n all over n plus 1 times -2 times -1/2. What is that? It's just 1, right? So 1 to the n minus 1. 1 to any power is just 1. So really all we have is the sum of n over n plus 1. And if you do the nth term test on that thing, you're going to see it's divergent. Okay, so note nth term test gives the limit of n over n plus 1. That's just 1, right? Because you're just taking n over n. That's not equal to 0, hence it's divergent. Okay. If it doesn't equal 0, it's divergent. If it equals 0, it doesn't mean anything. It means try something else. Okay, let's try 1/2. So again, I'm plugging in x. So I get the sum from n equals 1 to infinity of n all over n plus 1 times -2 times 1/2 is -1 to the n minus 1. This one is an alternating series, but it's going to fail the first step. So once you go to the alternating series, you're going to be like, oh, I need to take the limit of n over n plus 1. But you already did that. And it's not equal to 0. So again, you kind of go to the nth term test. And that gives us a limit of -1 to the n minus 1 times n all over n plus 1. This is the one where it goes to two different places, depending on whether it's even or odd, right? So if it's even, it'll be -1, and it'll be 1 if odd, which tells me that the limit does not exist, which is, of course, not equal to 0, hence it diverges by the nth term test. So ultimately then, your interval of convergence is the open interval from -1/2 to 1/2. Okay, and yes, you do have to show all that work if this is the case. You do have to show all of this work here. You can't just say it's divergent or convergent. You have to show me the work. Okay, I will take off points if you don't do it. All right. From there, finally, then we have 9.10. I'm going to skip 9.9. That was kind of like our backdoor way of building power series. We're just going to jump to the 9.10, which finally we see the relationship between these sequences of polynomials. If you take the limit of them, they actually, in some cases, equal the function that they were kind of created for. And so it sort of ends our exploration of sequences in series. So 9.10 then in particular, we're looking at questions like 5 to 15, 27 to 35, and then 63 to 67. So you have to know how to build power series representations, the Maclaurin and the Taylor versions, and then I expect you to be able to apply these to integrals. Okay? So in the first kind of problems, I will probably provide you with the formula for the particular functions. So for example, in number 35, they want find the first 4 terms of the series representation. Okay, so 35, they give you f of x is equal to cosine of x to the 3/2. Okay. So either I will give you the Maclaurin series for cosine x, or it'll be in a previous problem. Okay, so maybe those 9.7 problems, I'll give you cosine of x, and then you could sort of leech off of that work. Or if you have it memorized, you can just do that. But if I give you a weird one, like in my notes here, I have arctan, I'm going to look at next, I will give you the power series for it. Okay, so I'm not going to give you something you can't figure out, but one thing I will say here, do not try to take the derivatives of this thing. Okay, this is a substitution type problem. So you start with the cosine x, supposing you got it on a previous problem, or I give you the formula on the test, or you have it memorized. I just need the first 4 terms, basically. So this will be given on this problem or in a previous problem. Then you can find the cosine, the series for cosine of x to the 3/2, and this should go on and on forever, by just doing a substitution, right? So this would be 1 minus x to the 3/2 squared is x cubed, right? So to the side here, x to the 3/2 squared is x to the 3 halves times 2 is 6 halves, which is x cubed over 2 factorial plus x to the 4th to the 3 halves. X to the 3 halves to the 4 will be x to the 6 over 4 factorial. And again, if you have to, you just go over to the margin and figure that out, right? So this will be to the 4th. That's x to the 12 halves, which is x to the 6. And then minus x to the 3 halves to the 6 is x to the 9th over 6 factorial. And that's it. That's your answer. Right? There it is. Okay. And then for doing these integrals, I'll tell you how many terms to use in your approximation. You're not going to have to remember the Taylor's inequality or anything like that. So approx with the first 4 terms of the series. And let's look at 67. And this is one of the weird ones where I would give you the Maclaurin series, in particular for arctan. They want the integral of arctan of x over x dx. To get arctan of x over x, you just take arctan's polynomial and divide it by x. Okay, so as I said, I would give you arctan, so I wouldn't expect you to memorize that one. It's exactly like sine, to be honest, except there's no factorials in the denominators. So I'm only going to need the first 4 parts. Whoops, it also has alternating signs. Okay. So to get arctan of x over x, you just divide each one by x. So this will be 1 minus x squared over 3 plus x to the 4th over 5 minus x to the 6th over 7 plus blah, 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 blah. Then I need to integrate it. Okay, so I'm integrating this thing. This should be pretty easy. Once you get it here, you can do power rules on the polynomial. Etc. And we still have to evaluate it from 0 to 1/2. So when you plug in 1/2, you're going to get 1 all over 2 minus 1 all over, it being what? 2 cubed times 3 squared plus 1 all over 2 to the 5th times 5 to the 2. Ain't that a weird pattern? Minus 1 all over 2 to the 7 times 7 to the 2 plus and then minus, when you plug in 0 to all that, it'll all be 0. So basically you got it there. And then just do your approximation based off these first 4 terms. So you go to your calculator and you should get 0.4872. Okay, so definitely very interesting stuff. You know, the idea is that where do these functions come from, like sine x, and how do they relate to anything we've been doing with polynomials? Well, I think now you know, right? Basically, you could take a sequence of polynomials, like s1 is x, s2 is x plus x cubed over 3 factorial, or actually that should be minus, right? s3 is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And if you take the limit of that, you know, the limit of the sequence of polynomials as n goes to infinity, you will end up with, in this case, sine x. Okay. So that's kind of the relationship. How do we go from polynomials to trig functions and stuff like that? So hopefully you found this chapter 9 as interesting, or at least mildly interesting, as I do. Okay, thanks for watching. We'll see you next time, and good luck on the test.